what is logically happening in the sequence of events leading up to controlling the tank. I'll walk you guys through the code. So we'll just jump right in. So the first thing you'll see here is a bunch of, I guess, what looks like mumbo jumbo. It's actually a declaration of the pins. So it's basically saying that this pin maps to a certain motor driver pin, and this one, and this one, and this one, 22, 24, 26, 28, and pin number 5 is the PWM pin for the motor driver. Same thing happens for motor driver number 2. We establish what those pins are, and then over here we establish the input channel pins, so those channels are mapped to the receiver. And you can see here that I used pins 2, 3, 18, 19, and 4. The reason I picked 2, 3, 18, and 19 was because those are enabled interrupt service routine pins for the Arduino Mega. I could have done maybe a digital read and used some other pins, but interrupt service routines are ideal for this situation because it means we will not miss a pulse, which will make it far more responsive than if we were constantly pulling for the data. So we use volatile long to declare some of our variables. These variables will store the width of the pulse that we're measuring as transmitted by the transmitter and picked up by the receiver. They're declared volatile because they are used in an interrupt service routine. This is the maximum pulse width that you will ever receive from the receiver. This is the middle value for that pulse width, and then the minimum value for the pulse width. This ratio number here, you can see it. It is used in the algorithm for converting the pulse width into the appropriate motor direction and motor speed. So when we're talking about motor direction and motor speed, in terms of the control, it's setting certain pins high or low, and setting those pins tells the PWM motor driver, hey, rotate clockwise, or hey, rotate counterclockwise. And when we set the PWM value, we're setting it anywhere from 0 to 255. 255 would be 100% full voltage, and 0 would be off. And if you've not really read much about PWM or have much experience with it, it's not terribly complicated, but just think of a bunch of pulses that have an amplitude of, say, 5 volts, and if it is high for 50% of the time and low for 50% of the time, so 5 volts for 50% of the time, 0 volts for 50% of the time, the average value will be 2.5 volts, which will effectively change the motor speed. Big benefit to PWM is you actually are applying the full voltage, the full 24 volts, or in my little explanation, 5 volts, which allows you to have more start and stall torque on the motor. These data points here, these are variables that are storing the rising edge time, the falling edge time, and then the time difference between the rise and the fall. Next thing we have is the setup code. This setup sequence runs one time in the very beginning when the microcontroller is turning on, and it basically sets everything up to run smoothly for our main code. This line here tells us the clock rate of our microcontroller, what we want it set at. By setting this clock rate, it allows us to communicate with other things like a computer. If it's off in time, you'll just get a bunch of mumbo jumbo between the microcontroller and the computer. These lines create the interrupt service routines. So it says create an interrupt for this pin, channel 1 pin, which if we go up here, I think we can find channel 1 pin, which is pin number 2 on the Arduino, and it says look for a rising edge of a pulse, so we're going to look for the rising edge of the pulse, and if you see a rising edge, run this function. So it's pretty straightforward, and that will happen for all of the channels that we are pulling. This information here basically says, hey, these pins are going to be outputs, these pins are going to be inputs. You could actually change them at any time, but you do need to declare if they're going to be used as an output or an input for the arguments that are being passed. Then these next few lines basically just say, hey, our PWM motor driver should start in the forward direction, but it will start at 0 speed. And this is for a watchdog timer. This helps if anything's frozen, so if we don't come back to our watchdog timer every 1 second, it will reset the microcontroller because it thinks something's wrong and it's hung up in the code somewhere. So the first thing that happens then after the setup is the main loop. So the main loop is pretty self-explanatory. It loops through the code continuously. So we say, hey watchdog, we just looped through and it's less than a second, and it resets that timer so we can continue on. Then the next function that runs is the motor control. Now the confusing part is, since this is our only function, it seems, like this is the only thing that's running, but if you remember, we set up those interrupt service routines earlier that said, hey, if you detect a rising edge or a falling edge of a pulse on these pins, then we want you to do something. So we're actually always watching for that rising or falling edge for any of those pins. So if at any time we detect that, it will actually leave the main loop or the motor control function, and it will go and run those programs. So before we run motor control, we want to know where the thumbstick's set, and basically the signal is being transmitted to the Arduino at a constant rate by the handheld transmitter, and it's being picked up by the receiver. So say we received a pulse, so we would quick run and try and determine at what point in time we detected that pulse. So here is the interrupt service routine that's running after we detected the rising edge of a pulse for channel 1. So the first thing we do is we say, quick, what was the system time when we detected that rising edge? And then as soon as we check that system time, we attach an interrupt to that same pin, but this time we're looking for a falling signal. And so we wait, and waiting is actually running the main code. So the main code doesn't know anything happened until there's an interrupt service routine at which it's basically paused. It had no idea it was paused, and then you return back to where you were. So the next thing that happens is we detect the falling edge. So the interrupt service routine runs, and we detect a falling edge, and we say, hey, what was the system time when that happened? So for this example, we set channel 1 falling edge time equal to the system time. And then what we do is we take the falling edge time and subtract the rising edge time to come up with our time difference, which is essentially our PWM width. And that PWM width is then translated into a motor control function, and we can go check out how that works here. So as I was saying earlier, in the main code we're running these two functions, and we're actually running motor control all the time, but we're being constantly interrupted without us even knowing, which updates some information that we need in this motor control function. So now that we measured the pulse width, what happens is we do a little bit of logic to say, hey, was that pulse width less than the middle value for those pulse widths, which essentially says that if, say, is channel 3, it'd be the right thumbstick being in the down position or anywhere below the center neutral position. And if that's the case, we want our PWM signal to be proportional to however far that thumbstick is pushed down. So maybe if it's halfway to the bottom, we want it to be 50% speed, and if it's all the way to the bottom, we want it to be 100% speed, which is this 255 number. So the same thing applies for the if it's in, say, the middle position. We check to see if it's in the middle position, and if it's in the middle position, we want our motor to be off. We don't want it to be even inching forward or inching backward. We want that to be 0. But if, say, it's pushed slightly forward, if the PWM is slightly larger than our middle PWM value, then we want a proportional control saying, hey, if this thumbstick is forward or up, if it's 50%, if it's set to 50% in the forward direction, we want it to be 50% output. But if it's pushed all the way up, all the way forward, we want 100% output. And the same thing happens for both motors, that same logic. And additionally, what happens is after we determine that speed, nothing's been sent to the PWM motor driver. All we did is do the math to figure out what we want it to be set to and which direction it's going to be in. So after we do that, we run these functions. I have it commented out right now just for testing purposes, but normally it would not be commented out. So after we determined which direction the thumbstick is and how far it's pushed down, we quickly run to the appropriate function. So say it was pushed forward, we would run to the motor forward function, and if it's backwards, we would run to the motor reverse function. So the motor forward function can be found here, and as I was talking about earlier, we set certain pins to determine the direction of rotation according to the motor driver. So we set those pins on the motor driver, and then we tell our microcontroller, hey, we don't want interrupts right now because we don't want to corrupt our data. Because if you interrupt me now while I'm transmitting the data and the data changes while we're in mid-transmission, then we're going to have an issue. So we quick stop the interrupts, and then we write our PWM values, and then re-enable our interrupts. And the same thing applies for if we're going forward on the other motor, or going reverse on this motor, or reverse on the other motor. And that, in a nutshell, a very abridged, quick version is how the code works for the microcontroller system for controlling the tank motors.